Ronit has influenced my work and life in so many ways. So anyways, I'll say a few things about many aspects of how Ronit's work and mentorship has influenced my own work. But I'll start with the beginning. So I joined MIT in 2004, and I came from a liberal arts college. I had no idea about what sublinear algorithms were. MIT looked scary, but I was so inspired to enroll in Ronit's class, Sublinear time algorithms, which coincidentally was the first course that Ronit taught at MIT. So I went back to the lecture notes. It turns out that actually I do have handwritten notes from this course 20 years ago. And looking at the topics, I've learned a lot, of course. And just looking the other day at the topics, I realized that I have worked so far on pretty much every topic, almost every topic in that lecture. In that course. So that was an amazing realization. So anyways, I'll fast forward to my PhD thesis. So Ronit was not my PhD advisor, but BLR has influenced everyone's work, and in particular it's directly related to what I did during my PhD. So I did my PhD with Madhu Sudan, and I worked on locally testable codes. So this is an area that emerged from testing linearity. We can think of linearity as testing the membership in the Hadamard code. And the kind of questions people asked after realizing that we can test some code was what codes are testable. And of course, the seminal work of Ronit set the game for looking at other more general codes like Reed-Solomon codes, which are studied again and again and again, even like as we speak. We have local testers for Reed-Solomon codes with many nice trade-offs. Reed-Muller codes, BCH codes, multiplicity codes, all these nice codes that people use in coding theory turn out to be testable. Okay, so then people asked, oh, is there a unifying characterization of what codes are testable? Another seminal work of Madhu and Tali looked at symmetries, and in particular invariance under affine transformations and linear transformations. My PhD thesis essentially makes some contributions in coming up with very nice tests for some families of codes, like affine invariant sparse codes. It all started from the view that the Hadamard code has this very nice property that a test or the test for the Hadamard code can be generated from a single constraint that looks like that, 1b and 1 plus b, and all its affine transformations over f2 to the n. So this gets generalized into something called single orbit characterization, and many cool things can be extended from there. Okay, so another thing that I was very recently excited about and that I wanted to say a little bit about is the actual analysis strategy of the BLR linearity testing. So for those of you who are familiar with it, I'm going to just kind of quickly go over things. There is this kind of ingenious self-correction step. And in this step, so basically, the hard part is the soundness argument. And over there, people look at the counterpositive. So if the test accepts, then the received word is close to the Hadamard code. And the ingenious argument here is that they define the code word that the function that turns out to be the code word that W is close to. So in this self-correction step, one takes the majority of a bunch of votes and defines the function CW at A for every A. Okay, so then one has to prove that CW of A is close to W, it's close to W, and then that CW of A is itself a code word. And this is really the harder part. So what I wanted to get to is that this strategy has been used again and again to prove that codes are locally testable pretty much for all the locally testable codes out there. And I want to just emphasize this very cool recent result that kind of concluded a big question that there was in the literature, whether good codes that are locally testable exist. So good codes means codes that have little redundancy, but have a lot of error correction capabilities. And this result that came up a few years ago showed that such codes do exist. They could build such codes. So these are codes with constant queries, constant relative distance, and constant rate. And the amazing thing is that the same strategy from BLR actually is, there is a lot of more work, but the same strategy is what they follow in this kind of gold standard recent result. Okay, so I'm gonna jump a little bit to the next topic. I was lucky enough to have a paper with Ronit. So I remember we were having lunch at a conference somewhere in New York, and we were talking about polynomials. And Ronit asked, is your polynomial So she always asks good questions, right? So she asked, is your polynomial sparse or not? And I thought this was a very intriguing question because all the problems I had thought before about were these algebraic questions where you actually see kind of what the structure or what the test should look like, right? X, Y, X plus Y. But here for sparse polynomial, so sparse polynomial is a polynomial with very few monomials. So here, where do you even start? What sort of like a local characterization can you think of when you think about sparse polynomials? Anyways, we got this really nice paper. It's a very short paper, Schwartz-Zippel, and a beautiful characterization of sparsity using something called Hankel matrices. And basically we show that if that one can decide, so this is a decision question, one can decide whether F is L sparse or at least L plus one sparse with few queries and in little time. Okay, and this is a paper that somehow always often comes up in conversations. People tell me that they read it, and even Vipul here said he's working on something related. So I'm always excited to think about this paper. Okay, so here is another, I'm jumping to another thing. This is something I already talked a little bit about when last week when I talked about spanners, but as you know, Ronit, she's very inclusive. So Sophia was visiting MIT, was visiting Ronit at some point when I was a PhD student, and Ronit introduced us. And then Sophia told me about monotonicity testing and their wonderful papers. And then we figured out that there is this beautiful combinatorial structure called two-transitive closure spanner that actually can explain previous tests for monotonicity from the literature. And so basically the general result here is that for general process to test monotonicity, it's enough to make the size of the two-TC spanner over epsilon n many queries. Okay, and this gave us some very nice tests for minor free graphs. And in that paper, we also asked the question of whether of coming up with algorithms for building spanners. And long story short, now I have a student who's so excited about spanners. You probably heard so much about this topic, but yeah, it's interesting how this simple introduction led me to a student thesis 20 years later. So anyways, so it's hard to talk about Ronit without mentioning how what a fantastic mentor and role model she is. I can confirm that Ronit research with Ronit is super fun. It often goes around, involves food. It's often around food. We all know that she takes bad news with a good sense of humor. And she is kind, generous wise. I can say so many adjectives here, but gentle yet fearless leader, and someone who's really supported this community immensely. And I'll stop making her uncomfortable for a moment, and I'm gonna end with this quote of someone from the audience. So the backstory is we were at a conference. So a couple of Ronit students and we met, and Themis was her new student. So we all introduced each other. And at that point, Christoph takes a step back and has this revelation. So I think you will have a couple. So people got, all of us, the three of us, and Kevin got so excited. There are at least 4 versions of this picture with various characters put in that picture. And instead of Kevin was not here. So Christoph said he has another version of it. But yeah, happy birthday, Ronit, and thank you.
So much, and I have to make an observation that the heights were actually linear in that picture. I don't know if I'm sublinear, but the times were not linear.
So yeah. So Kevin claimed that was the only picture of him standing that he could find.
Other questions before Elena runs away? All right, thank you so much, everyone. This was a wonderful session. And please don't run away because we're going to take a picture. Where? That is a good question. I wonder if now that we have a natural step here. Yeah.